This video is going to show you how to draw an extended Freebody diagram. To begin with, I'll start with the simple body, and this body is being attached to the side of the building. So I have a building on the left, and I've got this beam being held up by a cable on the right. What I know about this is that the cable is a rope basically in tension on the end of the beam. I have this one new spot that's the center of gravity or the center of mass. Since we're talking about forces, we'll talk about it being the center of gravity, although for stuff that we're doing on the Earth, they'll be the same. And then on the left hand side, I've got this thing called a pin hinge. And the pin hinge is kind of a door turned sideways. So if you think of the beam as a door, it can swing up and down. That way when the cable expands and contracts due to weather conditions, it won't hurt the wall on the side of the building and won't pry any bolts loose. So now let's look at the forces on the beam. I have a rope, therefore I have a tension. So that's going to be pulling up on the beam. And then on the left hand side, where the pin hinge is, I have this thing I'm calling a reaction force. And the reaction force does two things. It keeps the left end of the beam from sliding down the building onto the ground. And then so that's supplying a vertical force. And then it also supplies a horizontal force pointing to the right. And that horizontal force is the normal force of the building. Without that normal force, the beam would punch a hole to the left going into the building. But that normal force of the building keeps it out that way. And when I add those two forces, the vertical and the horizontal force, they give me this thing called the reaction force. And finally, at the center of mass, that's where the weight of the beam actually acts itself. So I'm calling the weight mg. And I've got a couple distances that I'm going to make up for this problem. The first one's going to be the distance to the center of mass. I'll say it's 2 meters from the left. And I'll call the whole length of the beam 5 meters. All right, now let me slide up my beam a little bit so I can draw my extended Freebody diagram. Let's show you what it looks like on a piece of paper. This is what we normally draw as a Freebody diagram. We draw a dot and we say all the forces act right to the dot. But actually that's not what's going on. I've got this stick in the form of a beam. So now what I'm going to do is I'm going to draw an extended Freebody diagram as a stick. So I'll get rid of the dot and draw it as a stick. And now I'll draw the forces on the right correct places where they occur on the stick. So the tension, for example, is on the right hand side of my stick. And notice my stick looks just like the beam, just skinny. So there's the tension at its little angle. And then I've got the reaction force on the left-hand side of the stick and its angle. And then I've got the weight of the beam, which I'm calling mg, right at the center of mass. Now the one thing that makes this different from a Freebody diagram, besides the fact that it's a stick and not a little dot, is I want to also include distances. So any measurements I can find in the diagram, I want to include them on my extended Freebody diagram. So the first measurement is the fact that the beam is 5 meters long. And the second measurement is the fact that mg, or the weight of the beam, acts 2 meters from the left. And now my extended Freebody diagram is done if I'm an AP grader. So this is all we want to see. But just like Freebody diagrams, we would draw two of them. The second one we can find more useful because it's going to take R and T and break it up into perpendicular components. So with R, I'll make R the hypotenuse of a right triangle. And what I'm going to do is I'm going to draw R cosine alpha and then R sine alpha. And I'll do the same thing for the tension. So in this case I'll have T sine alpha, or T sine theta, and then T cosine theta. So it looks like it's almost complete, but since I'm talking about distances, I got to keep one thing in mind. When I draw these triangles, it looks like T sine theta occurs somewhere near the middle of the beam, but that's not true. That vertical component of the tension occurs wherever the tension touches the beam. In other words, T sine theta doesn't occur towards the middle, but it actually occurs towards the right, where tension touches the beam or the stick that I talked about earlier. And R sine alpha, that doesn't occur near the middle of the beam either. That occurs where R touches my extended Freebody diagram, or my stick. In this case, R is on the left side of the beam, so I'm going to slide this over to where R makes contact. So now it's all set up, and it's all done right with my extended Freebody diagram. When I start to actually use this to analyze the motion, this static equilibrium, and I start using torques, at this point what I would do is basically ignore my diagonal reaction force and my diagonally drawn tension and just deal with the forces and distances that I see on the screen right now.